Alright, today is Chapter 5, Section 1, Exponential Functions. Alright, so we've got, you can't really tell they're up there at the top, but we've got 40 of these pages to go through today. Normal sections are like maybe 25 tops. Today is going to be a very long one. It's going to be jam-packed with a lot of stuff.
Looks like it.
Yeah, it's going to be one of those days. But with that said, we will cover it all, and also if you need more of an understanding of this material, you can always look at my pre-calculus playlist, which also covers exponential functions, which was, I think we did it maybe last week or the week before last. Anyways, so without reading all the stuff up here again, I'll just put that on here for notes. The main thing I want to touch point is the definition here. Okay, so the definition of an exponential function is a function of the form f of x equal to b to the x power. Okay, where x is any real number and our base is greater than 0, and our base is not going to be 1. Okay, so the difference between us having an equation that looks something like this and an equation looking something like this, or function, okay, is that in order for it to be an exponential function, we must have the exponent be the variable. Okay, that's what makes these exponential functions. Alrighty, so this is just showing the basic uh, graph of a function. Right, so I'm sorry, of an exponential function. All right, so let's see here. The blue and the red line, they are right here, 3 to the x and 2 to the x. Okay, so these are the blue and the red lines. All right, notice how they are both whole numbers greater than 1. All right. Also notice real quickly that all four of these graphs, they cross 1 point. Okay, and similar to whenever I would talk about parent functions in the past and talk about the landmark that you moved around, and the landmark was typically 0, 0 for everything. The landmark for exponential functions is going to be the point 0, 1. Okay, so whenever we do transformations for exponential functions, they're all going to have this general shape. Right? The whole numbers shoot up exponentially, and the fractions shoot down exponentially. Right? But they're all going to cross the point 0, 1. Why? Because the point 0, 1, okay, if I were to plug 0 in for x into any of these x's, okay, anything raised to the 0th power is going to be 1. So that's why the point 0, 1 occurs in every single one of these exponential functions without any sort of horizontal or vertical shift. Okay, so 0, 1 is our landmark. All right, next we're going to talk about the natural exponential function. Okay, so the natural exponential function is going to be, doesn't say here. Give me a second. Let me see where it does say it so I don't get ahead of myself, if it even says it. Okay, well, this page doesn't seem to be loading. Let's try that again. Okay, so
Having some difficulties?
alright, this would definitely be a problem. Yeah, the textbook. Okay, there's page 10. Oh, there we go. Okay, so I don't know. The pages just weren't loading. Okay, so it doesn't actually call it the natural log. Well, because it's not the natural log. The exponential e. I guess it kind of does. Okay, so starting at this sentence right here, the number e is an irrational number that is defined as the value of the expression 1 plus 1 over n quantified are raised to the nth power. Right? The number e is very special and is used extensively in mathematics beyond this course. Well, beyond even the next course. So we use it. We use it quite often in calculus and of course differential equations. Right. So as you were to plug in values of n and the values get larger and larger as we approach infinity, then we approach this number right here, 2.71828. Right, 2.71828 is the number e. Okay, similar to how pi, right? Pi is a number, right? It's just designated as a Greek letter. E is also a number. It's just designated as another letter. All right, but it is a number, right? It's an irrational number, and it is 2.71828. So whenever at the end of the section, we're going to get to compounding interest problems. Whenever we talk about variables, many students will, just kind of autopilot and assume e is a variable, but it's not. Okay. That's about it for that. Okay, no, actually not really. Okay, so let's go back to f of x is equal to some base raised to the x power, right? This is just some exponential function. Typically, we'll have some number there for b, all right? But if we happen to have an e there, okay, well that's the same thing as saying, 2.71828 raised to the x power. Okay, again, it is just a number, right? It's just characterized as a letter. So that's that, hopefully. I always hate when I'm racing the clock. I feel like I miss things. Alrighty, so these are the characteristics of an exponential function. First of all, we talked about how if we, and here it is, if b is greater than 1, and if b is between 0 and 1, b being the base, right? If b is greater than 1, then of course we shoot up, like we said before. If it is a fraction, then we're going to be shooting down. Okay, but if it's equal to 1, obviously 1 raised to any power is just going to be 1. So that's why we see strictly greater than 1 and strictly between 0 and 1. Okay. Furthermore, we talked about why we cross that point 0, 1. Okay. And next up, let's talk about the horizontal asymptote. Okay. In both, let's talk about the domain range actually. So the domain of both these functions, okay, is going to be negative infinity to positive infinity. Okay, because obviously we go from way out here and we go up here, and we'll approach this way very, very slowly, but we will approach it given infinite time and infinite numbers. Okay, so that is the domain. It is from negative infinity to positive infinity. Now, the range, notice where this graph takes place. The range is going to be from 0 to infinity, but we're not going to actually be 0. Okay, we don't actually touch 0 anywhere. We get infinitely close, but we don't ever actually touch 0. Okay, so that's why my range is going to be from 0 to infinity. All right, so this would be our horizontal asymptote. All right, so 0 to infinity, not including 0, will be my range. It says the graph contains the points -1, 1 over b, and 1b. I mean, that's fine. Make sense of that as you will. I don't pay too much attention to that as I graph these. That should be, big deal here. Both of these functions are 1 to 1. Okay, that's a big deal leading into the next section. And that's about it for the characteristics of an exponential function. Again, just kind of memorize your general shape. And again, the domain is going to be the same, the range is going to be the same, the asymptote is going to be the same. Realistically, it's just, are we shooting up or are we shooting down? Okay, now for the easiest thing we're going to do today. And I'm just going to go ahead and snip all of this because this is a calculator problem. It reads, it is important that you're able to use your calculator to evaluate exponential expressions. Most calculators have the e to the x key. Find the special key on your calculator and evaluate the expressions in the following examples. So basically, again, just do as it says, calculate it, and see if you can get the correct answers here, okay? ABC. Yeah. If you you cannot find the exponential function, then talk to me, send a picture to me, or do a little research, figure it out on your own. But typically, you've probably used the key before, so it shouldn't be too hard. But again, if you can't figure it out, don't feel bad. Send me a picture, talk to me, let's figure it out, okay? Because if you can't do this, then we're going to be struggling big time moving forward. Okay, so next up, this reads sketch. So we're going to kind of mind sketch it, okay? Because that's kind of the point here. Okay, so first of all, A. It says sketch the graph of each. Okay, so all we have to do is sketch it. Okay, so we know the general shape of an exponential function. Okay, so let's see here. We'll do it like this, and we're gonna make A be red, and we're gonna make B be blue. Okay, so we know the general shape of an exponential function looks something like this. Okay, and let's actually denote that point 0, 1. Okay, that is the point 0, 1. All right, so again, we know the general shape of an exponential function looks like this. Okay, if our base is greater than 1. Okay, looking at A, the base is not greater than 1. The base is between 0 and 1. Okay, so therefore, we are going to be going down. Right, that is the general shape, and that is actually really beautiful, except for my elbow hit right here. Erase that over to the left. Right. Okay, so that is the general shape of A. Okay, B, it is a negative 2 e to the x power. So that base is a 2, so it will be shooting up like this, right? Okay, but we have to remember our transformation rules, because we do follow the transformation rules. All right, if we have the negative of the function, then we flip it across the x-axis, and of course we do indeed see that we have the negative of the function. So therefore, what we're going to do is we're going to flip this across the x-axis. So we're going to go this way, and we're going to cut through the point down here, and it's a 2, so we might shoot even faster. Okay, so let's denote this point real quick. Okay, so right here is the point 0, negative 1. Okay, well, if I'm flipping across the x-axis, okay, so if I'm above the x-axis and I shoot through the point 0, 1, that makes sense, right? But then if I'm flipping across the x-axis, then it only makes sense that I also go through the point 0, negative 1, correct? And that's what we did here. And obviously the shooting off, right, the slope of this exponential function is arbitrary as I draw it, because it is a 2, so I know that I'm shooting off faster. I say arbitrary. It's arbitrary in the sense that I might not be doing it perfectly, but I am doing the general shape. Okay, so this was A. And this was B. Okay. And of course, we see we have that general pattern, right? So everything that we learned about transformations, when I did maybe scare you into saying, hey, we have to do this just right. We have to remember how to do our transformations, because we're going to be doing a lot of this later on. This is what I meant. Okay, so this reads, find the exponential function f of x is equal to b to the x whose graph is given as follows. Okay, so what I'm going to have to do is I'm going to figure out what this function's graph is. Okay, how do I do that? Well, let's first of all examine the basic structure of an exponential function. Okay, and of course it's given to us, but there it is. Okay, so that's the basic anatomy of an exponential function. All right. Well, we also know y and f of x, y and f of x are essentially interchangeable, right? I mean, y is the function at x, right? So we have this. Okay, so we have y is equal to b raised to the x power. Right. So looking at this, just this structure here, we have one variable, two variables, and three variables. Perfect. Okay. We have 1, 2, 3. Well, looking at the graph that's given to us, we are given one x value and one y value, or number 2. Okay. So we're given 2 out of the 3 variables we need, and that's exactly all we need for us to solve this particular problem. Okay. So what we're going to have to do is we're going to say 9, let's do a better 9 there, 9/25 is going to be equal to b raised to the second power. Okay, and that's that, right? That is following along with that structure. I filled in my y, I filled in my x, so now I just have to solve for b. Well, in order to do this, I just have to do b is equal to, now if I take the square root of both sides, I would get plus or minus 3/5, right? That takes square root of both sides. Square root of 9 is 3. The square root of 5 is, the square root of 25 is 5. All right. Well, if I have to figure out what b is, and I have two possible solutions here, plus or minus. Okay. Well, let's go back to the very beginning. Okay. This definition states that b must be greater than 0. Okay, so that tells us exactly what this b has to be, and it must be the positive component of it. So it's just going to be b is equal to 3/5. All right, so excuse me. As I said before, the transformations that we did in 3.4, we're going to be doing the exact same things here. Okay, so similar to what I did then, if I added or subtracted to the parent function, it was a vertical shift. If I added or subtracted to the variable, it was a horizontal shift. And of course, we've seen the reflection about the x-axis already. So this page, it's there, but I'm not going to read it because it's things we've done. Just kind of a reminder. So example 4, this reads, use transformations to sketch the graph of f of x equal to negative 2x plus 1 plus 3. Negative 2 raised to x plus 1 power. Okay, so I said in 3.4 that there's always a first step if it's available, and it is available. That first step is always going to be the horizontal shift. Okay, and the horizontal shift in this particular case, we're going to be moving to the left 1 unit. Okay, and I always said that there is a last transformation if it's available, and that's the vertical shift. And of course, we do see a vertical shift, but we're going to do it last because we see a negative out front. Okay, so let's work on that. So if we have the negative of the parent function, so we're going to say reflect about x-axis. Okay, because we have that negative in front of my my parent function. So that's the second thing I'm going to do. And then the third thing I'm going to do is I'm going to make a vertical shift up 3 units. Okay, and I'm going to go ahead and put all that here. Again, yeah, that is the solution. And we notice how we have the horizontal shift first, we reflect second, we vertical shift last, and then we end up with our function that looks like this. Okay. we okay? It didn't ask for any x or y intercepts because let's actually take a look right here real quick. If we're solving for x here, right? If we want to find our x intercept, obviously, well, actually, this does have one because we transformed. Uh, but if we want to find our x intercept, notice how the x ends up in the exponent, right? And it reads, we now have a problem. We're going to need a way to solve this variable that appears in the exponent. Stay tuned for section 5.4. Okay, and I dare say that starting in this chapter, in my opinion, it actually college algebra gets easier because no longer are we doing tedious factoring and things like. I mean, we will be doing that, but it's not going to be just a mindless make your eyes bleed factoring stuff. Instead, it's more along the lines of we're going to be shifting things around to solve a problem. And so, in my opinion, that is just a lot more fun than again mindless computation. So I'm just going to go ahead and snip all of this. I feel like we should have a pretty good grasp on transformations. Nothing new here. We see that again. We have two potential transformations here. Okay, we obviously see the last one being a vertical shift, so we're not going to touch that until the very end. And then we have the negative of the function. All right, and the negative of the function, if you recall, is what we do is we flip it across the y-axis. And actually, this particular graph is not the solution, so I need to snip that because we are reflecting it across the y-axis as shown here. Now we'll do this. Again, sorry if I feel like I'm hand waving through this. Again, today's a long section, and I do feel like we have been doing transformations for a while. All right, now we get to the algebra of what we're doing. Okay, so everything that we've done so far is we just kind of dealt with the anatomy and the structure of exponential functions. Now we're gonna try to figure out how to solve exponential equations. Alrighty, so we'll start from the top. Let's see, anything good? All right, well, I will just read it. So one important property of all exponential functions is that they are one-to-one functions. Again, keep that in mind because we're going to be using that for the next section. You may want to review section 3.6. You're in luck. I actually recorded section 3.6, which discusses one-to-one functions in detail. The function f of x equal to b to the x is one-to-one because the graph f passes the horizontal line test. Okay, so let's go back and actually touch on that real quick. I mean, these are this would be an exponential function. It does indeed pass the horizontal line test. Okay. Notice how we do not cross that horizontal line more than one place anywhere in that function. So good, we pass the horizontal line test. And of course, here is an alternate definition of a one-to-one function that we've seen before. So this reads, using this definition and letting f of x equal to b to the x, we can say that b raised to the u power is equal to b raised to the v power, then u is equal to v, which makes sense, right? If I have 3 raised to x plus 3 power, probably stop using 3's, x plus 4 power, and that's equal to 3 raised to the we'll just say x plus 2 power, right? Well, the bases are the same, so therefore all I need to do is equate my exponents. And that's what we have down here when we are using the method of relating bases. Right? So if an exponential equation can be written in the form b raised to the u power is equal to b raised to the v power, then u is equal to v. Pretty easy stuff, but you are going to have to kind of think your way through it a little bit, and we're going to see that here in the next example. Okay. So putting that to work, starting with A, use the method of relating bases to solve exponential equations. So let's start with A. Solve the following equations. Okay, so let's go back and look at the related bases. Okay, so method of relating bases, it looks like we need to have the same base. Okay, that makes sense, right? But in A, we don't have the same base, so that's going to be a problem. Okay, so instead what we're going to do is we're going to manipulate it to make it to be the same base, right? And of course these are carefully chosen so we can, right? The method of relating bases is a special case that we're going to be talking about today. Later on, I guess it would be in 5.4, we're going to figure out how to solve all of these regardless of if the bases are related or not. Okay, so 8 and 16. 8 and 16. All right. What base raised to some power will give me 8 and 16? Okay, so that might be a lot to unwrap. So let's examine that. When I say what base can be raised to what power to give me 8 and 16, well, obviously, I won't say obviously, but the answer is 2. But let's go ahead and start with 3 real quick. Okay, since we know 3 is not going to be right. Now let's start with 4. Okay, so 4 raised to the first power is 4. 4 raised to the second power is 16. Okay, and then of course 4 raised to the third power is 64. None of these are 8 or 16. Okay, so 4 will not be the base there. All right, well, it's supposed to be eraser. All right, well, let's go down, let's use 3 now. Okay, so 3 raised to the first power, that's 3. 3 raised to the second power, that is 9. 3 raised to the third power, that is 27. Okay, same thing here. None of these give me the numbers 8 or 16. Okay, and of course I did say that it was a 2, but you probably knew that already as you were watching. Okay, so 2 raised to the first power, that's just going to be 2. 2 squared is going to be 4. 2 cubed is going to be 8. And 2 to the fourth power is 16. Okay, and of course we see the 8 and the 16 that is in our problem. Okay, so what we're going to do is we're going to have to rewrite the number 8 with the base of 2, and we're going to rewrite the number 16 with the base of 2. Okay, so this is how we do this. So rewriting the number 8 with the base of 2, as we saw, was pretty easy. It's going to be 2 raised to the fourth power. Okay, now 16, unlucky for us, is in the denominator, but let's go ahead and deal with it in the denominator real quick. So we said we can rewrite 16 as 2 raised to the fourth power. Okay, that's right, rewriting 16, and then it's all raised to the x power, right? Because it's 16 raised to the x power, and this, if I were to use my PEMDAS, 2 raised to the fourth power is 16, and this 16 raised to the x power. So all I do is simply rewrite this particular problem. Nothing extraordinary there. All right, so let's now go ahead and put it in 1 without any parentheses, because I do feel like that can be a little tricky. Okay, so there's that. So we have 2 to the fourth power. I'm sorry, it's supposed to be 2/3. Sorry about that. Over here it's supposed to be 2/3. We have 2 to the third power is equal to 1 over 2 to the 4x power. Okay, so let's actually, no, I think this could be confusing. So let's put an arrow there to essentially rewrite it. Okay, alrighty. So now we need to get our bases in my numerator. Okay, because again we have, going back here, if an exponential equation can be written in the form, again, they're both in my numerator, right? B to the u, b to the v. Okay, so, well, the 2 to the third power is already in my numerator, right? So we can just keep that there. But the other one is not. So how would I write the other one? How would I write this side with my base in the numerator? Well, recall your exponential rules, or I'm sorry, your exponent rules. Well, this would just be 2 to the negative 4x power. Okay, and if you forgot how to do that, go back and check out the prerequisite sections in this textbook. So now we have 2. Let's put a box around it. Now we have 2 raised to the third power is equal to 2 raised to the negative 4x. Right. So next thing we have to do is we need to equate 3, let's put it here, 3 is equal to a negative 4x, and then we just solve for x. Let's fix that 4 up a little bit. And then we just solve for x, so this is going to be, x is going to be equal to a negative 3/4. Okay? And that takes care of a. Right? So again, we had to do a little bit of manipulation to get that common base there, which is the 2. And then once we did that, we were able to structure our two expressions with a similar base and then solve by equating the exponents. And just so I have enough room, I'm going to go ahead and resnip example 6 so I can do B. I didn't want current page. Let's try that again. New page. Okay, so B obviously looks a lot more ridiculous, but that's okay. So looking at my numbers, my bases, it looks like I have a 27. And this, let's go ahead and change the fourth root of 3 to something a little bit more familiar. Okay, I know I can rewrite that as 3 to the 1/4 power. Okay, and that's raised to the x minus 2. Okay, so hopefully that makes it a lot easier to see that again we've got a 27 here and we have a 3 here. Okay, these are my two bases. Well, what is a base when raised to some power? That will go into both of these numbers. All right, we did it on the previous slide, and that would obviously be 3, right? Because 3 raised to the first power, that's 3. Takes care of that. 3 squared, well, that's 9, but 3 cubed, that's 27, and that is what we take care of here. Okay, so obviously 3 will be my base here. So let's go ahead and rewrite these. Okay, so I'm going to have 1 over, so it's going to be 3 cubed raised to the x power, right? And again, that's the same thing as 27 to the x power. And then on the right side, well, we already have that base of 3 in my numerator, good to go. So let's just go ahead and do our power rule here. And we know that the power rule, if we are taking a power and raising it to a power, then we're essentially just multiplying, right? So let's just go ahead and take care of that right now. So we're going to have 3 to the 1/4 times x minus 2. Okay, and we'll probably have to clean that up here in a moment, but let's just keep it like that for now. All right, and real quickly, while I'm just going to go ahead and erase it just for the sake of space, we know that 3 raised to the third power, raised to the x power, will be 3 raised to the 3x. So I'm going to go ahead and erase that and write that as 3 raised to the 3x. Okay. And obviously, like on the previous example, what we're going to have to do is we're going to have to put both my bases into my numerator. So I'm going to have a 3 raised to the negative 3x power, and that's going to be equal to 3. Let's just go ahead. Yeah, let's just go ahead and distribute this 1/4 here. So it's going to be 3 raised to the 1/4 x minus, and then 1/4 times 2, that's just going to be 1/2. So that's good. Okay, these 2's just aren't working. All right, that's good enough. All right, perfect. So now we have our equation. We have the bases are the same. Both bases are 3. So all we have to do from here is we just have to equate my my exponents. Okay, so let's go ahead and do that. So we're going to have a negative 3x is equal to a 1/4 x minus 1/2. All right. Luckily, we got lots of fractions. Let's just go ahead and clear the fractions. All right, I don't feel like dealing with fractions, so let's go ahead and clear the fractions. So I'm going to go ahead and multiply the entire thing by 4. So I'm going to have a negative 12x is equal to x minus 2. Yeah. Okay. Good. All right. Again, all I did was simply take this equation, and just multiply the entire thing by 12. Just clearing the fractions, right? Not 12, by 4. Sorry about that. By 4. Just to clear the fraction, right? 4 times negative 3 is negative 12. 4 times 1/4, that's just 1. And 4 times 1/2, that's just 2. Okay, so all I do is clear the fractions there. And if I were to solve for x, it looks like I could add 12x to both sides, so I get 13. And then I get, what, 2/13? So I would have x is equal to 2/13. Okay. And that's how we solve these. Oh man, that was only those two. Okay, we have a lot to go. All right, so I might have to tone down a little bit of the explaining as we move on to example 7, but it is going to be the same principle here. Yeah, it's the only difference would be that we are using e, I guess. Well, that's not the only difference, but it's the major difference. Okay, so let's go ahead and start with a. Again, luckily the left side is already written like we want it, right? 3x minus 1. The right side, let's just go ahead and do this in our head, right? Let's go ahead and do this in our head. So 1 over e, nah, we won't do it in our head. We'll do it down here. Square root of e, we know 1 over square root of e, well that is the same thing as saying 1 over e to the 1/2, okay? Well, if I want to get that e to the 1/2 into my numerator, I'm going to write e to the negative 1/2 like so. Okay, and that's really it. And then from there, we just equate 3x minus 1. We're going to equate that to a negative 1/2. Okay, and of course that's not the solution, but we're going to go ahead on to b. All right. Again, I feel like this, guys, that's pretty easy stuff, so I'm not going to touch it. Next up, we have b. All right, so we have e to the, oh, this is pretty good, e to the x squared over e to the 10th, okay? Well, we need to have both these bases in my numerator, so again, let's recall our power rules here. And so we can rewrite this left side as e to the x squared minus 10 power. Pretty easy. Okay, again, I just take my numerator and I subtract my denominator. Okay, and then the right side is e to the, and then it's x times 3, or we know it as 3x. Okay, and similar to a, I'm not going to solve this. Instead, this looks like a quadratic that I'll have to deal with and solve from there. Okay, so I feel like example 7 there was a lot less manipulating than for example 6, so that's good. We're not going to do that one. All right, so compound interest. Excuse me. All right, here we go. So many of you might have taken stats, or you're going to be taking stats. This is just a part of it. Little problem from it, but it gives an example of how we use exponents as well as our number e, right? I don't think we actually use e on this one though. But anyways, so this reads, a real-life application of exponential functions is the concept of compound interest. That is, interest that is paid on both principal and interest. First, we take a look at how simple interest is accrued. If an investment of P dollars is invested at R% annually, okay, so let's go ahead and real quick, let's take mental notes here. The P represents the initial investment, and its R is going to be my my rate of my my interest, right? And it's percent annually. Okay, so keep that in mind, annually. And it says written as a decimal. So what does that mean? So real quickly, if I say something is accruing interest at 7%, then writing that as a decimal would be 0.07. Okay, so that is a very big mistake that many people do make, but you won't, right? Using simple interest, then the interest earned after 1 year is PR dollars. Adding this interest to the original investment yields a total amount of, and then we see our formula there. honestly, let's be real. I don't care about that. I'm only saying that because the big one that we're looking for is going to be on the page after this, but I will still snip this because it is interesting to see where this comes from, but it's not worth the lecture time, in my opinion. Instead, this is what you come for, I'm sure. Okay, so unfortunately, this is going to have to be memorized. Okay, but real quickly, let's go ahead and examine. Well, actually, we don't have to because it's already given to us. Okay, so looks like we have one. Oops. Looks like we have 1, 2, 3, 4. Looks like we have 5 variables here. Okay. Well, when we have these interest problems, you're going to be given 4 of them. And I'm pretty sure for this section, it's going to be all of them but the a value because as of right now, we don't necessarily have the tools to solve something if my variable is unknown, or I'm sorry, if my exponent is unknown. Okay, we will gather those tools soon, but we don't have them right now. But anyways, so we have 5 unknowns. All right, A is the total amount after 2 years. So A is how much you have after all things is said and done. The P is your original investment. R again is the interest rate per year, and the N would be the number of times interest is compounded per year, and T would be number of years. Okay, so there's not much else to say about that. You have 5 variables, but you're going to be given 4 of them. It's your job to figure out what those 4 are. Right? So let's go through and do a problem, and I'll try to do this the way. Well, I mean, I guess that's the way I'd still do it now. But I was going to say the way I made sense of it when I was taking college algebra, and again, when I was taking college algebra, I was not going into mathematics, so I was done with this, right? Okay, so first of all, this reads, which investment results in greater total amount after 25 years? Okay, so let's rewrite our formula. Was it organ and T? Okay, let's rewrite the formula there. Okay, and real quickly, while we're at it, let's go ahead and put A is equal to P is equal to R is equal to N. That's a very righteous looking N, and then a T. Okay. So real quick, let's go ahead and denote investment A is in red and investment B in blue. Okay. So first of all, the A value is actually what we are trying to find in both of these because we're trying to figure out which investment gives the most back after so many years. Okay. So investment A looks like we are investing $12,000, and investment B looks like we are investing $10,000. Okay. The rate of investment A is 3%, so we would write that in the decimal form as a 0.03. The rate for B would be 0.039. Okay. Now again, if I were to put 0.3, right, that is 30%. Okay, so don't do that. Just try to slow down and think about what you're writing down. So A. All right. So both of these actually. Well, let's go in order. Okay. So N would be compounded monthly. So how many months are in a year? That's pretty easy. It's gonna be 12. And then for the blue one, compounded quarterly, there are 4 quarters in a year, so that's going to be a 4 there. And then lastly, the time is the same as well because they're both after 25 years. Okay, and that's it. Once I figured out what goes where, and let's center these up a little bit better. Once I figure out what goes where, I just plug and chug. Okay, and so I'm just going to go ahead instead of writing it all. I'm just going to go ahead and put the solution out like this because it really is just simply figuring out what you're plugging in and plugging it in. Okay. So it appears if we plug everything in and everything works out just right, then it looks like investment B will yield the most money after 25 years. So if I invested $10,000, after 25 years I'd have $26,386, which isn't which isn't bad, I guess. But after 25 years, I'd hope to make a lot more than $16,000 off of a $10,000 investment. But then again, I guess it really, if I invested, if I invested $1 million, that would be a quarter million in interest. But still, this is how we calculate compound interest. Just write down, like I did, write down what goes where. Do that first, and then go ahead and take those and plug them in as you proceed. Right? It'll be a lot easier. All right, so now we have continuous compounding interest. Okay. So this reads, some banks use continuous compounding. That is, they compound the interest every fraction of a second every day. So instead of like on the previous example, we compounded monthly, compounded quarterly. Some banks compound continuously, meaning again every second every day. So it just every fraction of a cent is being compounded. Okay. If we start with the formula for periodic compound interest, which we have, and let n, again, which is the number of times interest is compounded each year, we let that approach infinity, we can derive the formula a is equal to PERT. Okay, so this is probably not the first time you have seen a is equal to PERT, and that is the formula for continuous compounding interest. So let us look down here. A equals PERT. So real quickly, again, if after 46 minutes, because even like I don't care who you are, you hear about math for 46 minutes, you check out. But if I were to, ask somebody, hey, how many variables do we have here? One might mistakenly say 5, right? I say mistakenly because, as I mentioned earlier, I'm not even pointing at the E is a number. It is not a variable. Okay, so instead we only have 4 variables. Okay, and similar to the previous problem, if you have 5 variables, we will be given 4 of those unknowns. For continuous compounding, if we are given 4 unknowns, but we are given 3 of those unknowns, then it's easier to solve. And of course, I'm pretty sure again, like on the previous example, we're going to be solving for A most likely in this section. Obviously, later on, we will be solving for other things, but again, we don't actually have the tools to solve for things when my variable, my unknown, is in my exponent. So A is equal to PERT. Okay, so similar to the previous problem, let's do this. Okay. And then let's it looks like there is only one problem here, so that's good. Meaning that we don't have P. Almost wrote the E there. R T. Okay, so the amount, that's what we're trying to figure out. The principal looks like it is $6,000. My rate is at 4.5%, so that is written as 0.045. And then my time, it looks like it is 5 years. Okay. And that's it. We just have to plug these in. And again, I'm just going to go ahead and put this in here. Just plug and chug, plug in our P, our R, and our T. And so we see that we have $7,513 continuous compounding interest, and it yields 11 cents more interest after 5 years. So let's see. Is this the previous problem? Okay, yeah, it is. It says compare this to the amount to the same investment that was compounded daily. Okay, so if we invested 6,000, well, hang on, I mean that's 4.5% though. That's a lot more. We can't really compare that. Either way, there you go. so another formula. Now, I'm pretty sure you have to memorize these formulas. Okay, so real quickly, go go with the idea that you have to memorize the formulas. Okay, however, you might be given if I recall, you might be given the formula on the exam. All right, and of course, I'm not going to get your hopes up because, well, here's the thing: if you're given the formula on your homework, then you'll be given the formula on the final exam. Okay. Uh, Also, I don't know if I said this or not. Kind of off topic, but the final exam is multiple choice. All right. So if you struggled mightily with the midterm, that is the hardest test you'll have in this course. The final exam obviously would be comprehensive, but it's multiple choice and it's the easier toned down version of everything you learned. So I don't know if I've said that, but there. Anyways, present value. So let's read. Sometimes investors want to know how much money to invest now to reach a certain investment goal in the future. This amount of money, P, is also known as the present value of $A. To find a formula for present value, we start with the formula for periodic compound interest and solve the formula. All right, so obviously we do our algebra. And again, this kind of harps back to whenever I derived the quadratic formula, right? These formulas aren't just um, sprouting up from somebody sitting in a dark corner putting in p's, a's, and negative n's and t's. All right, these are done just using simple algebra. And of course, using our algebra, we for periodic compound interest, if we were to solve this for p, then we end up with the formula p is equal to this. Okay, and that's also known as the present value formula for periodic compound interest. And of course, we will have probably a nice box. Yeah, so we'll put this on the next page. And again, it's our present value formula. Same thing. All of these are the exact same. Okay. The only difference is that previously we had this, right? It was the amount is equal to all that good stuff, right? Instead, now what we did was we took this equation and we solved it for p, and so we get p is equal to. Okay. So all the variables are the same thing. And then, of course, we also have the present value for continuous compounding. So real quick, because we have a lot of these, let's go ahead and talk about them real quick. Okay, they're broken down. They're really just broken down two of these. Okay, one of them would be the periodic compound interest, where we compound periodically. The next would be the continuous compounding. Perfect. Okay. Well, this present value stuff is just basically taking the periodic compounding and solving for p, and the present value for continuous compounding is we take the continuous compounding and we also solve it for p. Okay, so realistically, it's just those two formulas, but instead of solving for a on the present value, we solve for p, which makes sense, right? P, present value, all that good stuff. All right, so I think those 40 pages were on page 35. So this reads, determine the present value. We're going to find the present value of $8,000. All right, so this is compounded quarterly, perfect. So compounded quarterly, let's go ahead and, all right, so we're going to start with A. My compounded quarterly is, first of all, yeah, all right, it's going to be P, present value again, is going to be equal to A, and we're going to be 1 plus, we're raising it to a negative nt. Okay. So similar to how we solved these problems before, let's go ahead and denote what goes where. All right. So first of all, it says find the present value of an $8,000. Okay, so $8,000 is going to be my A. Interest paid at a rate, so my rate is going to be, this is definitely going to be a two-pager. My rate's going to be 5.6%, so it's going to be 0.056. Compounded quarterly, so my n value quarterly is going to be 4, and then my time is going to be 7. Okay, so we take all these, and so we have P is equal to 8,000, 1 plus R over, so R is 0 point, that's a horrible 0, 0.056 all over N, which is 4, raised to the negative NT power, which is a negative, so NT is 28, right? So negative 28, and oh man, let's go and do this. $54.20, and it says the nearest cent, so 5,420.35. Okay, so that's A. Again, plug and chug. Okay, B. Okay, we're going to structure this the same way we did A. So B, if I were to use, I have to use my formula, it's going to be P is equal to A e to the negative RT. Negative RT, yeah. Okay. And then let's structure it the same. So we're going to do A. Wait, how do I do it? A R T. Oh, there's not an N, that's why. A R T. Okay, so find the present value of $18,000. So that's going to be 18,000. If interest paid is at a rate of 8%, so 0.08 over 20 years. So same thing as before. P is equal to 18,000. E, that's horrible. Let's fix that 0. E raised to the negative RT, so we'll do 0.08 times 20. All right, here we go. 18,000 raised, or no, times E raised to the negative 0.08 times 20. So we have 36, 34, 14. 36, 34, 14. All right. Again, guys, it's just plug and chug. It's nothing extraordinary. Again, we're not doing any sort of mind-numbing factoring or distributing or any of those things before. It's just basically move things around and or plug and chug. Oh my goodness! All right, so page 36. I said I think we go to 40. So exponential growth. Now this is just a jam-packed section. Holy cow! All right, so you've probably heard that some populations grow exponentially. Most populations grow at a rate proportional to the size of the population. In other words, the larger the population, the faster the population grows. Makes sense? With this in mind, it can be shown in a more advanced math courses that the mathematical model can describe population growth as given by the function P of t is equal to P naught times e raised to the kt. Okay. Now, I will take this time to say that yes, population does grow exponentially, but only at first. Okay, and we might see it a problem like this in the next section with logarithmic, but I feel like logarithmic growth is more, I won't say better, but it models population growth better, at least for the long run, right? Because again, while I'm on this subject, and I think I have a few minutes, if we were to grow exponentially, right? Well, if you were to model Earth's population, then by 2100 we'd have like 8 trillion people. Okay, so that's what I mean by yeah, things do grow exponentially, but there's a certain point where it just kind of falls off, and we no longer start growing exponentially. And of course, that has to do with space, food, I don't know, diseases, things like that. So that's why things don't typically stay the exponential growth. But anyways, with that said, the exponential growth. A model that describes a population p after a certain time t is, and I'm pretty sure you're not have to memorize all these, so don't fret too much. But anyways, that is our formula where p naught is equal to p of 0. Okay, p of 0 is the initial population, and k greater than 0 is a constant called relative growth rate. Okay, so k is a constant that should be given to us most of the time. If not, it's just a short hop, skip, and jump away to actually solve for k. Okay, but this is our exponential growth model. Okay, all right, so yeah, this is a good example. We are given a lot of stuff here. So let's begin. This reads, the population of a small town follows the exponential growth model of p of t is equal to 900 times e raised to 0.015t, where t is the number of years after 1900. Perfect. So it says answer the following questions. All right, so what was the population of this town in 1900? Okay, well we could do this in our head, right? If t, so it says t is the number of years after 1900. Okay, well at 1900, how many years after 1900 is 1900? Well, it's 0 years after, right? Because 1901 would be 1 year after 1900. So 1900 is 0 years after 1900. So we'd put a 0 right here for t, and then a 0 times anything is 0. Anything raised to the 0th power is 1, so e raised to the 0th power is going to be 1, and we'd have 1 times 900. So that's pretty easy, 900. Okay. And then B reads, what was the population of this town in 1950? Well, we're going to have to plug in 50 for t. So we're going to have p of 50, right? P of 50, because t is our variable there. Right? Normally we are using x's, right? X's if we're in the more abstract mathematical world. But now that we're venturing into the real world, our variables actually mean something. In this particular case, t is time. So p of 50 is equal to 900 e raised to 0.015 times 50, and that is 900, ooh, that's 9,000, times e raised to the 0.015 times 50. It looks like 1905. So we have 1,905 people. So in 50 years, we grew our quaint little town from 900. We grew it about 1,000 people. Okay. C, what uses model to predict the population of this town in 2012? Okay, so again, it's going to be 2012 is 112 years after 1900, so we're going to do p of 112, and that is equal to 900 e to the 0.015, and so this should be easy. All I got to move that or change that 50 to 112 on my phone. 4829. And real quick, let me try something real quick. Okay, so I mentioned how exponential models break down, and this is a good example. Okay, now this particular town, obviously, I'm sure is fictional, whatever, right? But if a town in any town followed this particular growth model, okay, well, after 50 years and after 112 years, we have decent looking numbers, right? Well, let's say the year is 1020, okay, exactly 1,000 years ago. I'm pretty sure there were towns with 900 people, and I'm pretty sure there were towns with 900 people that might have had close to this growth rate. Well, after 1,000 years, using that same model, then that town would have 2.9 billion people in it. Okay, that one little town would have 2.9 billion people after 1,000 years. Okay, and obviously, I mean, the world right now has close to like 7.5 or 8 billion people. So obviously, a town growing, a town of 900 growing to a little under half the total world's population after 1,000 years. Hopefully, you see now where these models break down. Okay, they do work in context of the shorter time frame, but as you grow into the larger time frame, it does begin to break down. This is page 38. So we're almost there. Alrighty, so 20 years ago, the Idaho Fish and Game Department introduced a new breed of wolf into a certain Idaho forest. The current wolf population in this forest now estimated at 825 with a relative growth rate of 12%. Okay. Use the exponential growth model. P of t is equal to p naught e raised to the kt power to answer the following questions. Round each answer to the nearest whole number. Okay, so A. How many wolves did the Idaho Fish and Game Department initially introduce into the forest? Okay, so we're going to have to figure out how much they initially put into the forest. So what we're going to have to do is we're going to have to make, let's go ahead and write. Oops. Okay, so it's wanting to know how many we initially introduced into the forest, okay? And so P naught, if you recall, is my initial number, right? So we're going to have to plug in our values and figure out exactly what is P naught, okay? So in order to go about this, and this is definitely going to be a multi-pager, we're going to have to, okay, it says 20 years ago, so it looks like time is going to be 20, and we have 825. Okay, so as of right now, we have 825 wolves. Okay, we don't know what P naught is. We have to solve for that, and we have e raised to the k was already given to us at 0.12, and then t we're going to say is 20 because, again, it took me a second to read this, but real quickly, how did I get that 20? Well, this reads, how many wolves did the Idaho Fish and Game Department initially introduce to the forest? Okay, well, we are 20 years after the fact. That's why. Okay, so that's where I get that 20 from. So now all I have to do is solve for P naught, and if I do that, so first of all, e raised to the, this one is 825, okay, because what I'm going to do, obviously, algebraically, I'm going to get what this number is, and then I'm going to divide both sides by it, right? So I'm going to go to 825 divided by e raised to the 0.12 times 20. So it looks like, oh, it's not, times 20. About 75. Okay. Now, real quickly, I had to do a double take because when I put this into my calculator, and I do feel like, I mean, the calculator is going to calculate what you put into it. So let me see if I can replicate it real quickly. Okay. So what I did initially was I wrote in my calculator, I wrote 825. I had a divided by symbol, and then I like to put things in parentheses. So I put a parentheses e, and then I put a caret 0.12, and then I did times 20. Okay. Now that looks like it would be the case, right? It looks like it would be what I should put into it. But my calculator, when I look to see what it's actually doing, and put it into my familiar division symbol like this, it actually did this. Okay, which is obviously not the same, right? Because that 20 needs to be multiplied up here by the 0.12. So I had to check that out and go back. So instead, what I should have done, and what I eventually did do, was I also put parentheses around this. Okay, And again, it's a mistake I make. I'm pretty sure it'll be a mistake that you might make. So be careful with that. And yeah, I guess I'll erase all that. I feel like it just jumbles it up. Anyways, that would be A. So we initially put 75 wolves into the wild. It's a lot of wolves. Okay. Next up, we have B. So it reads, how many wolves can be expected after another 25 years? Okay, so now that we have my initial number, right, which is 25, so let's go ahead and once again let's write our formula again, because I like to write underneath it whenever we figure out. Oh, I did that there. Yeah, I like to underneath it whenever I figure out what I have where. P naught. Okay. So how many wolves can be expected? So what is going to be after another 20 years? So that tells me that T is going to be 40 now, right? Because we're 20 years after the initial drop, and how many years after 20 more years? Okay, so this is going to be P of, we're going to say 40. Okay, T is going to be equal to 40, and that's going to be equal to P naught, we said, was 75. E raised to the K is going to remain the same at 0.12 times T, which is going to be 40 total. Okay, it's 40 total again because I'm 20 years. So my initial drop, my problem is taking place here. Okay, so this right here is 20 years, and then it wants to know in 20 more years. So 40 years total. Okay. And the algebra there, again, just simple plug and chug. 75 e raised to the, I'm not going to make that mistake again. I'm going to go ahead and put 0.12 and 40 both in a parentheses, well, by each other. So we should have 9,113 wolves after 20 years. Okay, and I think that's, oh, yeah, 9,113 is 40 the, oh, wow. Okay, so I went a little bit faster than I probably should have because we still have 13 minutes left. But hopefully I didn't go too fast to where the lecture was just kind of jumbled up. But anyways, that does conclude today's lecture.